Fantastic. So I assume all of you guys are here for learning about maps. I am Zain, and today I will be your instructor for the next 3 hours or so as we take a beautiful and magical journey through some maps. So how I set up this tutorial is there's really no exercises or anything like that. If you guys want to follow along, you can try, but I wouldn't necessarily recommend it. One of the problems with tutorials of this nature is that everybody's at a completely different skill level, and trying to get everybody on the same page is incredibly difficult. And on top of that, the toolchain that we're using is actually kind of a pain to install. So I didn't really want to put all of you guys through that. And so I formatted this such that you can watch me follow along with what I'm doing, take notes. I promise to throw all the code and all of the slides and all of that up on the web afterwards so you can take a look at it. And I will be completely open to, like, if you want to email me with questions or anything like that at any time, that's totally fine as well. But hopefully, if I did my job right, you don't need to actually follow along on your computer with your own code. But you can try if you want to. So a good way to start out, I think, is by taking a look at the end. I read that in a book called The 7 Habits of Highly Effective People, which is actually a terrible book. But it says, habit 2, begin with the end in mind. So let's take a look at what I want us to implement while we're here. Yeah, that'd be great. If we could turn these lights off, at least up front, that would be awesome. Sweet. There's still a couple more, if that's possible. I do want to show up on the video. All right, so this is what I hope we can implement by the end of the tutorial today. What you're looking at here is the top right corner of San Francisco. Each individual point, the little yellow dots, are individual. Oh, that was over there. Got it. Each yellow point that you see is an individual crime in San Francisco. And underneath all of those crimes is a heat map of those crimes. So red means it's a dangerous area. Green means it's a fairly safe area. And there's a linear scale between the two where orange is kind of okay, and so on and so forth. The interesting part is all of these are actually vector dots, so they're clickable, and you can see what the crime that was actually committed was. So these are not like rendered images. And this is real data, by the way, as reported by the SFPD. So what you're looking at here is roughly 10,000 or so points on the map at one time. And it's still reasonably performant on my MacBook Air, which is also generating all of this. So we won't cover performance too much, but the hope is that we can make something that's not horribly slow. So that's what we looked at. And there's really three parts to building this out. I like to call it the map sandwich. It's 3 different layers that are put together in the front end in the browser, and they're all generated individually on the back end. So the three different layers are: 1, the points, the individual crime dots; 2, the heat map, which is generated images on the back end and sent to the front end; and then there's the base map layer. It's a styled layer underneath everything that shows you the roads, that shows you BART stations, things like that. But before we dive into it, let's take a step back and let's talk a little bit about cartography and what that means. And this might be a review or refresher for some of you. If I move too fast here, please raise your hand, ask questions. I really like questions, and I try to cover everything a little bit and hope that people will ask me to go deeper in stuff that they want me to go deeper. So please don't hesitate in asking questions. Cartography. Cartography is the study of making maps. It's the art and science of maps. Back in the day, people had these giant canvases that they drew all over what they knew was the world. And that's when the study of maps was first created. These days, a common term that's thrown around is GIS, Geographic Information Systems. And that's the intersection of cartography, making maps, with database technology and statistical analysis. So the combination of those three things, where you have geodata, often large amounts of geodata, that you want to put on a map somehow, and you want to do some sort of analysis on it so that it's easier to understand and easier to grok. That's what GIS is. So the basics of cartography, I'm sure you guys know what a latitude and longitude are, but just in case you don't, they are what define the grid that makes up our world. You can define any unique point on the globe by a pair of latitude and longitude. Latitudes are the lines that go east to west. They are parallel to the equator. And longitudes are the ones that go north to south, from the North Pole to the South Pole. These days, we don't quite draw maps anymore. We use Slippy maps. I'm sure you guys remember the old days of MapQuest, when you had like the tiny little image that you were looking at, and to pan across the map, you'd click like left, 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 and slowly inch forwards to where you wanted to go. These days, with Slippy maps, we're able to drag indefinitely and see the entire world at our fingertips. And that was pioneered by Google Maps when they first came out. It kind of changed the world when they created this, the cartography world at least, because for the first time, your map did not have boundaries. You could just drag all the way. You could zoom in, see more detail, zoom out, see less detail. Completely changed the face of cartography. And so Google Maps is Slippy tiles, and really any Slippy tiles that you see these days are made entirely possible by the concept of map tiles. So this is an incredibly important concept that I will explain to you now. Map tiles are a way to split up the world, basically. Say you have a paper map in front of you. You want to be able to chunk that into pieces. That's basically what map tiles do at different zoom levels. So taking a step back, we're looking at the geography of the world on a 2D plane. And we need to break that up into manageable chunks, hopefully with the boundaries always being the same. How do we do that? We start out with the entire world on one tile. So this is the highest zoom level out. At zoom level 0, you're looking at the entire world, and the entire world is one tile. This tile is 256 by 256 pixels. It's almost always that size. It can be different sizes. It is almost always either a PNG or a JPEG. And you're looking at the entire world on this little image. As you want to move closer into the image, as you want to zoom in, the next zoom level in, zoom level 1, is 4 tiles. That one tile at zoom level 0 is split up into 4 tiles at zoom level 1. And so on and so forth. As you continue zooming in, you break each individual tile into 4 tiles at each zoom level. And so you exponentially increase the number of tiles that you have. You exponentially increase the amount of detail that you have. And this is basically the basis of Slippy maps. Let's take a look at a demo to make that a little bit clearer. So this is I'll throw these URLs up in my slides, by the way. But this is a demo that shows off the different formats of tiles. We really only have to worry about one numbering format, and that's the Google one. So you can basically ignore TMS, you can ignore quad tree. And what you're looking at here is a normal Slippy map that you know and love, that's zoomed out all the way, and so the entire world is on one single tile. The JavaScript library that's showing this to us it loops it on the left side and on the right side. So we're really looking at only one image. That's this entire image. But as we pan around, it repeats itself. Now when we zoom in here, as we'd expect, this one image is going to be broken up into 4 images. So these 4 images, top left is 0, 0, bottom right is 1, 1. And just like before, they repeat. So this is 0, 0 here, still 0, 0 here. This is zoom level 1. At zoom level 1, we have 4 tiles. And we can define, we know exactly which tile is represented by 0, 0 at zoom level 1. We know exactly which tile is represented by 1, 1 in zoom level 1. And we're able to go from those coordinates, from knowing which tile we're at, to a bounding box. Because this is split up the exact same way no matter what. It's a simple algorithm. So say somebody said, I would like a tile, I would like the 1, 0 tile, this one, at zoom level 1. We can derive exactly what the bounds of that are in latitude and longitude. We know exactly what the top left point is of this tile in latitude and longitude. We know what the bottom right is. We can calculate that ourselves. So why does this matter? Well, you don't really need to know most of this because most of the libraries will handle it for you. But it's kind of similar to if you're using an ORM, you should know that it's backed by a database. You should know how that works, why that works, that sort of thing. And so a lot of this complexity is completely shielded from you with the libraries that you're using. And it's a global standard, so you really don't, you only need to know this once. The standard is called the Google ZXY format. And it can be used to represent any sort of tiled data on the world. Yeah, speaking of which, you can actually store data tiles this way as well, which is getting a step ahead of ourselves here. But say you wanted, say you had a list of restaurants in your database, and you wanted to tile that list of restaurants. You could access it rather than a .png, you'd access it as a .json or something. Using this, this format, you'd want the restaurants in tile 0, 0 at zoom level 1. You know what the bounding box is. You can get the restaurants for that bounding box. But we'll go into that in more detail later. So the important thing to understand here is that each individual tile is unique based on its zoom level, its x coordinate, and its y coordinate. So just like we saw 0, 0 in the last example, this is 2,608, 5,859 at zoom level 14. And this is a tile of Portland. In any mapping library, in any tile set, basically anything that follows this format will have this river in this exact same square at this coordinate. And that's the beauty of this. It converts bounding boxes and latitude and longitude sets into integers, which can then be thrown into a URL, for example. So if I wanted to access this tile on Google Maps, if I knew the base URL for their CDN, I could just plug this in and see that individual tile as one PNG that, if I was to load up maps.google.com, would get pulled into their JavaScript library and rendered as I dragged along. Yep. No, so it has nothing to do, well, it does not represent anything with latitude and longitude. It represents this x and y coordinate that we were just looking at. Yeah, so like the 0, 0, 0, 1, or 1, 0. So we can actually zoom in further here and see that now this is split up into even more tiles. So if we wanted this, x would be 4, y would be 3, z would be 3. Uh-huh. So the question is, why is there not a complete URL on this slide? Why is there, what do the 3 dots represent? Yeah, that was just to save space. It represents a server. So this could be maps.google.com/tiles/this. This is an interesting demo of tiles. Imagine that the red rectangle is your viewport that you're looking at on your screen. Each of the gray squares represent an individual tile. And as you pan around, the browser fetches the new tiles for the place that you're looking at and flushes out the tiles for the places that you're not looking at anymore. This is basically how Slippy maps work in the world. Each one of those tiles is a chunk of roads, of highways, of rivers, of trees, baked into a PNG or a JPEG. And the front-end JavaScript library fetches that and shows it to you when you pan over to it. So this is a really important concept. Is everybody following so far? Cool. So what do you actually put on those tiles? Well, there's 3 data types that are specific to maps. You can put anything you want on a Slippy map. You can put a JPEG. You can put, it's a canvas. You can draw on it if you want. But there's 3 data types that are specific to maps that are implemented in most map libraries and most toolkits that you'll find. And those are points, lines, and polygons. Point, as it implies, is a single latitude, comma, longitude coordinate pair. You have to be careful there. If you notice latitude, comma, longitude in a normal graph system is y, comma, x. So it's the horizontal axis, comma, rather the vertical axis, comma, the horizontal axis. Whereas a lot of geometric systems expect x, comma, y. That's what we learned in Algebra 1. And this will bite you if you do any amount of GIS work at all, because some things accept x, comma, y, and some things accept lat, comma, lon, which is y, comma, x. And at some point, you'll try to input the coordinates for San Francisco, and you'll wonder why your map is centering in the middle of Africa. And that's when you'll think back to my words, and you'll reverse the order, and I will have saved you hours and hours of work, hopefully. So map libraries can take raw geodata in these formats. You know, they're still latitude and longitudes. They're not pixel space. They're not anything specific to the browser. It's raw geodata. Libraries can take it and display it on a map without much interaction from you, thanks to these data types, basically. Most libraries also provide the multi-versions of these. So actually, let me explain these data types first. Points are latitude, comma, longitude. Lines are a collection of points that are connected. And polygons are collections of lines that are connected, usually closed. And like I said, most libraries provide multi-versions of these. So multi-points are an array of points that are disjoint. Multi-lines are an array of lines that don't necessarily create a polygon. Multi-polygons are collections of polygons that may be somewhere related but are disjoint. So for example, if you wanted shapes of the United States, you would use a multi-polygon because the continental United States would be one shape, Alaska would be another shape, Hawaii would be another shape, Hawaii would be like 8 shapes. So that creates a multi-polygon. All of this brings us to our data store, which is Postgres, which is a database like MySQL if you're not familiar, and PostGIS, which is a excuse me, which is a set of extensions on top of Postgres that geo-enable the database. So it's not a hosted service or anything. It's something you actually compile, you build on top of Postgres, and it provides you those data types that we just talked about. So just like you have a character field, you have an integer field, you have floats. On top of all of that, you will now have a point field. You will have a polygon field. You can create lines. You can do queries on those fields like you'd expect. You can look for example, if you have a database full of points, you can find all of the rows that are within 1 mile of a certain point. You can find all of the points that are within a particular polygon. It basically makes it so that you feel like Postgres natively supports geoqueries and geodata. Speaking of databases, your other options are generally not as great as Postgres and PostGIS. You can use SQLite. There's a set of spatial extensions on top of SQLite that let you do the same sort of queries. It doesn't support nearly everything that PostGIS does, but it's a good stopgap. MySQL is horrible with geodata. MySQL's support consists of, say you wanted to do a query. For example, you have a bunch of zip codes in one table, which are polygons. You have a bunch of restaurants in another table, which are points. Say you want to find all of the restaurants within a particular zip code. MySQL's queries will use the minimum bounding rectangle, which is to say it'll draw a box around the zip code polygon that you're querying for, and then it'll query for that box. It'll essentially be a less than or equal to float query, where it gets the top left and the bottom right and finds all the latitudes and longitudes that are between those 2 points in a box. So it doesn't actually do a real point and polygon search, which is one of the many things that it does not do. So basically, if you want to do geo things with MySQL, you're probably better off just using float fields and implementing it yourself. MongoDB has some spatial extensions. I've played with it a little bit. It also doesn't support as much. I guess it's fine if you already have a MongoDB database or something and you want to spatially enable it. But it also, for example, until very recently, did not support point and polygon searches. And it's still very new. And the JavaScript libraries that we'll be using. The JavaScript libraries are the things that run in the browser that show us the Slippy maps, that are responsible for fetching the tiles, that show us the tiles, that are responsible for throwing markers down, that are responsible for overlapping all of the different layers that we're loading. Lots of different things, that some of which we don't even know what they are yet. Let's run through our options when it comes to JavaScript libraries. So Google Maps is, of course, the biggest and the most well-known JavaScript library. Pretty much mostly everyone in the world has used it at some point. It is quickly losing steam these days for a couple of reasons. One of the main reasons, which you may have heard on the Hacker Newses these days, is the fact that they have started enforcing their license. So they have started charging a fair number of their customers a very large amount of money. In a lot of people's opinions, it's a ludicrous amount of money for the value that they get. And so people just switch off of Google Maps. Big examples of that include very recently Foursquare, who no longer uses Google Maps, and Apple. When they announced the iPad 3 yesterday, they also announced iPhoto. And in iPhoto, historically, they've always used Google Maps, but for the very first time, they have switched to OpenStreetMaps and no longer use Google Maps in any way, shape, or form. So it's important to note here, while we're talking about this, the difference between the JavaScript interaction library and the underlying tiles, the underlying map itself, the roads, the streets, the lakes, forests, all of that. Those are two very different things. And when people say Google Maps, they talk often about the combination of the two. So there's the JavaScript interaction layer, which when I click and drag, handles my clicks, which show this zoom dialog, which show these arrows. That's the JavaScript interaction layer. It's very different from the tiles underneath. These things, which, like we've established, are 256 by 256 pixel images. The images can be used separately from the JavaScript library. And so if I wanted to use Google Maps, the JavaScript library, with Bing's maps, I could actually do that. Probably don't want to do that, but you could. So whenever I'm talking about Google Maps or anything like that, I will try to make sure to say which part I'm talking about, because they're very two different parts. Does that make sense? Cool. So again, talking about Google Maps as a whole, both the JavaScript library as well as the tiles themselves are not as popular a choice these days as they were before. Luckily, there's a slew of options that have popped up that are in many ways better than what Google Maps offers. Bing is not one of them. It's another library that's similar to Google Maps, where you have the combination of a JavaScript library and a tile set. Most people don't like the tile set as much as Google Maps. Most people don't like the library as much as Google Maps. And you're still beholden to the big corporation. So let's pass over that. MapQuest. You guys remember those guys? They went quiet for a while, and more recently they've actually been kicking ass quite a bit. Not so much in their JavaScript library. It's still in its infancy. But in terms of their APIs, they provide a stupid amount of data for no charge with no restrictions. So we'll go into that a little bit later. But something to keep in mind, that MapQuest also has a JavaScript library. The one that we'll be using today is called Leaflet. Leaflet is a fairly new JavaScript interaction library that came out of a company called CloudMade. So again, Leaflet is just the interaction library. It has nothing to do with how the roads look, where they're placed, how the labels look. It does have to do with what controls are on there. So you can tell that the zoom button looks different here than Google Maps. It does have to do with the speed at which things load when you drag or when you click. The reason that we're using Leaflet, a couple of reasons. One, it's considerably faster than Google Maps when using a ton of markers. So for the crime maps that we're about to make, we're throwing 10,000 points onto a map. That's a lot of points and a lot of little red Google Map markers. Google Maps slows down a lot more than Leaflet does. Secondly, the license thing, it's on a lot of people's minds. Even though you might not get big enough to worry about it for a little while, if you're starting a new project, it's enough of a worry that you might want to not use Google Maps. And thirdly, it's a lot more flexible. Leaflet is actually really cool. It lets you do really interesting things like style your markers using CSS3, style your controls using CSS3, style everything using CSS3, except for the underlying base map. The interesting part there is you can do all sorts of things like use CSS3 animations. You can make your dots pulsate or blink or marquee all around. So this is the library that we will be using today. This is the JavaScript library that will combine our 3 map sandwich layers. A couple more things that are worth covering as well. There's a library called Mapstraction. This, as it implies, abstracts out all of the different mapping libraries. And so you can say, Mapstraction, load Google Maps. You use the Mapstraction API to build your map. Later on, you can say, never mind, give me Leaflet instead. And without changing any code, you can switch from Google Maps to Leaflet. It's really cool in that way. You can switch between, they support like a dozen different tile sets and 5 or 6 different libraries. It's really nifty to use. The problem is you lose the fine-grained control that you get out of all of these libraries. Each of these libraries has different strengths, different weaknesses, and mapstraction, by its definition, is the lowest common denominator. So if you're throwing vanilla markers on a page or just loading a vanilla tile set, then it's fine. But for anything more complicated than that, you really want to pick a library and stick to it. Wax is a similar concept. It's a library out of a really interesting studio called Development Seed. They make a popular program called TileMill, which hopefully we'll look at later on in this tutorial. They're incredibly intelligent, and it shows from their documentation, which is basically posts on a WordPress blog. So their documentation really sucks. But the point of this is to support really interesting things like rasterized data. Now that probably means nothing to most of you. It barely means anything to me. But the interesting thing is you can do things like this, where you mouse over a country and you can see the map of that country. Normally, you'd have to send ridiculous amounts of data to the browser. Basically, you'd have to send the exact shapes of a million different countries and figure out this where you're clicking in the browser, which is ridiculously slow. Drawing that many polygons is way too slow. They invented this interesting tool called UTF Grid, which lets you get around that by basically drawing a map in text. And we'll go into that in more detail later. So anyway, the point of Wax is, again, to not abstract out the APIs of all the different mapping libraries, but to provide stuff on top that is unified. So you still use the raw Google Maps or leaflet controls and APIs, but on top of that, you can use a unified API for something like loading GeoJSON in. I'm not a huge fan, by the way, of either of these libraries. They're worth knowing about, they're worth playing with, but they add a lot more complexity for not a lot of gain. Anyway, going back to the map sandwich, I think we're just about ready to start diving into code and playing with it. Basically, my plan here is to set up a fresh database, set up a fresh project, and run through everything, and build this entire thing on the fly. As I go through, I'll come back to the slides, and we'll learn a bit more, then code a bit more, and learn a bit more, and so on and so forth. We'll actually start with slides here as we look at the dots layer. So here, many of you, some of you, maybe all of you, have thrown dots on a map before. It's fairly simple to do, but it's surprisingly difficult to do when you have strict requirements on the back end for loading a lot of data, and you have strict requirements on the front end for putting a lot of data on a map. So I'll go through a little bit of that. And first, I will tell you about GeoDjango. How many people here are familiar with Django? Cool, so most of you. Some of this might be repeat, but I'll go through it quickly. GeoDjango is an extension on top of Django that geo-enables Django, essentially. So with Django, you get this nice ORM, this layer on top of your database that lets you talk to the database in a very Pythonic way. GeoDjango spatially enables that ORM. So your database is now smarter, your database understands geo operations. Django doesn't yet, so you add GeoDjango on top. There's room to make that framework smarter. The old way of doing things in Django, if you wanted to do anything spatial related, you'd either have to drop into straight SQL and run those queries yourself, or you'd basically create those columns that are of type float, one for latitude, one for longitude, and do those calculations yourself. But thanks to GeoDjango, we can do interesting things. Like on this model, this is a Django model for a restaurant. It has 3 fields, a name, a rating, and a point. the point represents where that restaurant is. The name and the rating are standard Django fields, but the point itself is a GeoDjango field, and it's represented by a point field in the PostGIS database that's backing this. So let's see what it looks like to actually query this database. Here we have a point. We want to find the restaurant that is at that point. So we can do restaurant.objects.filter point equals here, which will get us the restaurants that are at that point. We can go even deeper into this querying and do a more complicated query like, I want to find all of the restaurants that are within 1 mile of here. If you're not familiar with Django's query language, the double underscore is a way to add a modifier to your query. So here we're filtering by point underscore underscore distance underscore less than. And we're looking for all of the points that are at a distance of less than 1 mile. The D object is a magical object provided to you by Django for distances. So you can pass in something like kilometers or meters into that as well and say, give me all of the restaurants within 1 kilometer of here. There's a whole set of these modifiers that you can do. For example, distance greater than, less than or equal to, so on and so forth. I'll throw them in the slides at the end. I'll throw a link to the docs for those, but it's all pretty well documented. We can do more complicated things. I mentioned this example earlier. We have a table full of zip codes, which have polygons attached to them, and we have a table full of restaurants, which have a point attached to them. We want to find all of the restaurants that are within a particular zip code, so we do this query. We do zipcode.objects.get poly, which is the name of the field that contains the polygon, underscore underscore contains, which is another one of those modifiers, this point. Right, so we define them as models in our Django configuration. And so they are 2 different tables in the database. There's a zip code table, there's a restaurant table.
You said you're actually getting restaurants in zip code, you're getting offset, right?
I did say that, sorry. That's the next example. The question was, why did I say that we were getting all of the restaurants in a zip code? Because we're not. We're getting all of the zip codes that contain the restaurant, which is namely 1 zip code. So to say that again, zipcode.objects.get will return you a zip code that contains the restaurant point. Let's take a look at the opposite example of what I was saying before, which is we have a zip code, 94105, that has a polygon attached to it, and we're trying to get all of the restaurants within that zip code. So we can do a filter such that the restaurant point is within the zip code polygon. And that's what I was talking about last time. Yeah.
Talk about the distinction between within and
Sure. So it's the opposite. A point would be within a polygon, whereas a polygon would contain a point. So a point can't contain a polygon. That make sense? I can go back over these again if anybody's confused.
Are these models set up ahead of time with relationships to one another, or can you do this dynamically without pre-setting up code?
Yeah, this is entirely dynamically. So there's no like foreign key relationship or anything between these. They're 2 different models, two disjoint tables in the database, and we're joining them on the geo fields. So that's roughly what we need to know for GeoDjango for the purposes of this tutorial. We'll go a little bit deeper into it as we code, but we'll take it as it comes. And by the way, if it isn't clear, this is an ORM, so this is actually translating this into a query, which is sent to the database in the back end and return. So this is still backed by PostGIS and Postgres. Cool. So So I think it's a good time to start coding. Yes, I like Adele. Now you all know. All right. So I have a folder here with some data in it. I'll go into more detail on all of this stuff afterwards, but basically we have shape files that contain block data, all of the blocks in San Francisco. We have a gzipped JSON file that contain crimes, something like 9,000 or 10,000 crimes for San Francisco. And we have shape files that represent the water around San Francisco. I'll explain why the water is there later. You'll see. So I'm creating a brand new Django project here. And to start out with, there's a bit of standard setup that we have to do that I'll just breeze through here real quick. We have to change our database engine to use PostGIS instead of Postgres. Can everybody read that all right, by the way? Cool. It's the name of the database, the username to access the database, password is blank. Set a directory for the templates. In installed apps, we add django.contrib.gis, which is GeoDjango. And then we go and create the database. We called it map tutorial Python. So the createDB command is a command in Postgres. The -t template PostGIS, that part is actually part of configuring PostGIS. That it creates a when you configure PostGIS, you create a template called template_PostGIS that contains all of the data that Postgres needs to be able to do these geo queries. The static data like how long is a mile, for example. Tons of other stuff on top of that. So by saying that we want to create a database based on that template, our map tutorial PyCon database will have all of that data in it as well, which means it'll be geo-enabled and we can do all the nice stuff that we want to do. Create a database. Go into the folder with the Django project. We run syncdb, which is a Django command to basically synchronize your models with the database. This actually runs SQL to create tables and all that. And then we can run a development server as soon as I kill my old one. Run server creates that development server listening on localhost 8000. And hey, we have a basic Django project working. So I think a good place to start, since we're showing crime points on a map, is to actually load those crime points in. Before we can load them in, we have to define what that table looks like in the database by defining some models. So this will create a Django application that will hold our crimes. As you can see, in extremely tiny text, we have a new folder called crime and a models.py created under it. So here we're creating a crime model. And then afterwards, we can load in the crime data into that model. First things first, we have to change this import The default import is not for GeoDjango, it's for Django Vanilla. That's what you have to do to change that. All right, so we have a few fields on this crime model. We have a crime type, which is a character field of length 50. We have a date time field, which contains the date and the time of the crime. And we have a description. That's a description that we saw when we were clicking on each of those individual dots. That's provided to us by the data source. And finally, the GeoDjango magic, we have a point, which is a point field. That's where the crime happened. Now, a little bit more boilerplate you need for GeoDjango. You have to override the default objects manager. If you don't know Django, it's just something you have to do. If you don't do this, your queries, when you do something like crime.objects.filter by point within some polygon, if you try to do this without this line in there, you'll get all sorts of weird errors because you're actually using Django vanilla, that manager, rather than the GeoDjango manager. And for the string representation of the crime, we'll just return the description. Cool. So this is our basic crime model. Don't think we need anything else in there. We sync it to the database running syncdb. Actually, one more thing we have to do before that, which is add this new app that we created, Crime, to our installed apps. And there we go. We created the table, crime_crime. And I can directly load in the crime data set that I have in data called crimes.json.gz. Now, that's not any magic. Before this, I pulled this data from a site called Crime Spotting, and I formatted it such that I could just easily slurp it in. We'll talk a little bit later about how to take arbitrary geodata and load it in, but you can basically use Django's standard object creation methods, crime.objects.create or crime.save, to create these things. Just in the interest of time, I did that already, and so I'm just going to load in these crimes. By the way, I write a lot of bugs, so if you see one, just yell out. Kind of wanted to bring candy or something to throw at people who found me writing bugs. Cool. About 1,000 crimes loaded into the database. Let's load up a shell and take a look at what that looks like. So we have our crime app that we created first. We have models underneath it. And we have the crime model underneath that. We have the 9,962 crimes that we saw loaded into the database. And we can filter on anything that we want. Let's say, So what we just filtered for here was on the field date underscore time, which as you remember is when the crime happened. We have a date object D, and we looked for all crimes that happened after this date. So it was about half of them in our database. This is over a period of like 2 months, by the way. Cool. So everybody following so far? If so, we're ready to start creating a template and actually looking at this, creating a view after that and actually looking at this. No, totally. So the question is, what is this shell that I'm in, and how do I magically have access to the ORM? And the answer to that is, it's really just a normal Python shell. There's nothing that's done to the namespace. There's nothing that's magically added in. You remember that I created a Python package called crime when I ran start app, which we have right here. So it has in a .py script, maps.crime, and then under that we have a models file. And so this model that we just created is actually under crime.models. And so I just imported that. If you remember, I overrode objects. By default, since this is inheriting from Django's model, it has a default objects manager on it, and that's what you use to actually make queries. So you go through that objects manager. We overrided it to make it geo-enabled. And when we do crime.objects.filter, filter is a method on that manager that lets you do those queries. Cool. All right. Not that I know of. I actually believe, and somebody can correct me here if I'm wrong, subclassing a model, for example, if I was to subclass this crime, if I was to do something like that, I would actually have to override the objects again because that's how Django's model works. So if I don't have this here, it will actually default to Django's default manager, and so doing geoqueries on another crime will fail. This is interesting. Sorry, I forgot to repeat the question. The question was, is there a GeoDjango model that I can override here that will automatically set objects? The answer was no. All right, so we're making URLs. Let's do something like crime. You guys can watch me Google for docs. I always forget that path. So this is a view that will just render a template directly. We're going to create the template in a sec. Does that make sense? And we're going to create monstrously long lines. All right, so this is the URL conf for Django. In short, we have this URL path /crime. It will be passed off to this view, which is a very simple view that is included in Django that will basically take an HTML page and spit it out. And the HTML page that it'll take is called crime.html. If you're not familiar with Django, crime.html should be in the template directory, which was previously defined in settings, which we defined as templates. So at the same place as settings.py and the same level as the crime folder, we have another folder called templates. Under templates, we have crime.html. And that's what we're going to be editing. And hey, we have a template. So it's time to dive into HTML and JavaScript land for a short while until we get a map up and running, and then we can throw those points onto that map. So I will breeze through a lot of this boilerplate. I can actually just copy paste this. All right, basic so far. We have a title. We included a style sheet from Leaflet. By the way, Leaflet is hosted on a CDN, which is nice. So you don't actually need to save it on your own machine. You can just access it directly from their servers. For actually using Leaflet, you include a single style sheet and a single JavaScript file. All right, boilerplate. We included jQuery. Leaflet doesn't actually require jQuery, but we have it. And we have the actual Leaflet JavaScript. Actually, close the head. All right, so the hope here is we want some sort of a map to show up in map div. We have a document ready function, which will be run when the DOM is loaded, when the page is loaded. And we want, when that happens, we want to load up a map div with some sort of a map. So to do that, we first create a map object. The L object, by the way, is Leaflet. And I will actually pull this from the Leaflet docs, so you know I'm not just pulling this out of my ass. The example right here does that sort of a thing. And I will explain all of this in just a sec. Code everywhere. All right, so what do we have here? Let's take it one step at a time. That's better. All right, so we want a map to show up in the map div. That's the div that we defined up here. We added a new tile layer. So this tile layer is the base map. This is the path to, basically, the path to the tiles that are in the format z/x/y.png, the 256 by 256 pixel images that we talked about. And each one of those images contains roads and streets and all that good stuff that makes a map. So this creates an object called CloudMade that represents this tile layer. We have to actually add that to our map. We set the viewport of the map to a point. This is a point. And a zoom level. And we'll get back to everything in a sec. Let's just see what this looks like. Oh, by the way, the div is actually tiny, so I will make it bigger. There's a leaflet quick start guide, which is fantastic for copy pasting code like this. Huzzah, we have the beginnings of a map. All right, for starters, I'm just going to make this full screen. This is some simple CSS to make the map be full size rather than stunted. Now we have a full size map. And drag around. Leaflet gives us this zoom control for free. Does not give us a fast internet connection for free. All right. By the way, as you can see, those little squares loading in, those are tiles. Alrighty. Let's take a look at this really quickly. Wow, it's a huge URL. So that URL, as you can see, it has a few curly braces in it, which will be replaced by CloudMade. I'll explain what those are in just a sec. But the server is tile.cloudmade.com. If you remember earlier, I mentioned that CloudMade is their business is creating maps that look better than your default maps. So to that end, they provide a set of free tile sets here being that base map that you're looking at with the roads and all that. They provide a set of those for free that generally look a little bit better than Google Maps, or they have less information on them or different colors, so you can show your data, make it pop a lot more. In the final crime maps that we're making here, we will actually be using one of CloudMade's styles called Midnight Commander, which was that nice dark blue base map that we saw up there. In this case, the default that Leaflet shows off in their demos is one that's less dark, I guess. So the server here is tile.cloudmade.com. This is an API key, pretty standard. 997 is the style number of it. So this is all still boilerplate. You don't need to worry about any of this. 256 is the size of it, not important. This entire thing is basically the base URL for your tile set. Now where it gets interesting is this last part. We saw this format earlier. This is the path to the tiles. And our interaction library, Leaflet, will automatically fill in these values. So while we're at zoom level 13, Z will be replaced by 13. As we pan over, X and Y will be filled in by the X and Y values of the tiles that are being fetched into the viewport. Each one of these objects has a set of options that you can pass in. So in this case, there's an attribution option that will go down on the bottom right here. If you can see that, it's tiny text. Often, depending on what data source you have, they require attribution. That comes in handy once in a while. Max zoom. It's not really that necessary, but it'll limit the amount you can zoom in to zoom level 18. Just for simplicity, I will probably take both of those out. And once again, we add this layer to the map. We can add other layers on top of this, below it, so on and so forth. We set the view to define where the map centers first. And in this case, it turns out it centers at this point, zoom level 13. I will change that point to San Francisco. The lat long for that is right there. Now we're looking at San Francisco. Cool. Hopefully this is pretty straightforward so far. Any questions? Fantastic. We can start getting into the fun part, which is figuring out a way to get the data from our backend. You know that our crimes are stored in a Postgres database right now. Figuring out how to get that data to the front end over here so that we can add a new layer to this map containing the markers of the crimes that we want to show. So now is a good time to tell you guys what GeoJSON is. JSON, as you may know, is a data serialization format that is commonly used by back-end people to send data to the front end. Things like if you wanted to send tweets from Twitter's backend to the front end, the JavaScript would request JSON and then render that JSON in the front end. Similarly, GeoJSON is a specific format of JSON. So it defines what the key names are supposed to be and in what order they're supposed to be. And once those things are defined, it's a format, you can just pass in GeoJSON to any of these libraries and it'll understand where to find the information that it needs. So for example, if you want to pass a set of points, crime points maybe, from the back end to the front end, GeoJSON is a great way to do that because you don't have to code in the logic in the front end that says, all right, dig through my dictionary, this is the key name for the point. The first one is a latitude, the second one is a longitude. All that logic is handled for you. The library will do that because it knows what GeoJSON is supposed to look like. So the first task is on our backend in Python. We create a view that fetches all of the crimes that we want to see in the bounding box and returns it in a GeoJSON format. So let's see what that looks like. We're going to open up crime/views. It's traditionally where the views go. And if you're not familiar with Django parlance, a view is the function that is run when somebody actually hits your site. The view function is actually run. It gets a request, it returns a response, that response goes out to the user. So this is a request, and we have to return some sort of a response here. Let's start with this. So first we figure out what the bounding box is. Each request will come with a bounding box. As we pan around, we'll want all of the crimes in this area. Then we pan over here, and we'll want all of the crimes in this area, and so on and so forth. So every single one of these requests will come with a bounding box that defines what the coordinates of the top left and the bottom right are. So first we want to figure out what that bounding box is, so we know what chunk of crimes that we're returning. Then we want to fetch those crimes from the database. We want to convert them to GeoJSON. And finally, we want to return the response. That's basically what we're doing in this view. So first things first, to figure out what the bounding box is, the easiest way to do that is to just accept a get parameter. So it's a get parameter. It'll look something like yes. So somewhat. We're actually going to be making that request in using jQuery, but Leaflet can provide us the bounding box of what the user is looking at right now. So spoiler alert, we're going to call map.getBounds. You guys remember the Leaflet map? That'll get us the bounds. That comes later. And so that'll look something like, that request will look something like vbox equals And this string is what will be stored in this request variable. What this string represents is the minimum value of the minimum x value, the minimum y value, the maximum x value, and the maximum y value. So based on that, we can calculate the bounding box of this request. So we'll split that on a comma. So bbox will be an array of 4 numbers, which hopefully look like a bounding box. Now we're going to use a something from GeoDjango called a polygon object. All right, and we've created a polygon object from this. We're about to use it to actually make the query. You can't actually make the query using just an array of numbers. You have to actually create a polygon object in Django, and you'll be doing the query on that. It's really similar to, for example, when you do a foreign key lookup in vanilla Django, you don't just pass in like the ID, you actually pass in an object. Similarly, here you pass in a polygon object. And this function, polygon from bbox, it takes in those numbers and spits out a polygon object. This polygon object actually has a lot of other interesting features as well. Things like you can expand out the polygon if you wanted to. There's a function that will, it's called buffer, that takes a number and will expand out the polygon by that number. And so if you wanted to make the polygon bigger, for example, you could do that. If you wanted to, instead of even using the polygon, you could just get the centroid of the polygon. So for example, if the polygon represents a neighborhood of some sort, you could get the centroid of that neighborhood, buffer that centroid out, like we were just talking about, and basically have a circle that surrounds the center of the neighborhood. So interesting things like that to help with your querying. We don't need to do any of that. We have a simple box. This polygon has 4 sides. It's easy to understand. All right, this is, that's odd. This is our actual query. We get all the crimes that are within the bounding box polygon. Now we are going to convert to GeoJSON. And it's worth taking a look at the GeoJSON format. You Google for GeoJSON, it's the first result. And this is what it looks like. It looks like a, I'll make this bigger. Looks like a normal JSON object, but with specific names. So at the top level of this dictionary is a key called type, which is called feature collection, and then an array of features. So in mapping parlance, a feature is basically a geometry. So it could be a point, it could be a polygon, it could be a line, any one of those things. They're called features as a whole. Under the features array, we have a dictionary of that feature. Each feature has one additional thing that you might not expect, which is a dictionary called properties. That's where we're actually going to throw our description in. You can basically, it's a dictionary that you can put whatever you want in there, and the front end will have access to that. And the most important part is, of course, the geometry. Ours will also be of type point, and our coordinates will hopefully be x comma y. I don't even remember. I told you guys, it's horrible. We'll try both. All right, so our GeoJSON dict will look something like this. I'll fill in features in just a second. Come back to that. I'll actually return a response here first. All right, so if you're not familiar with Django, HTTP response is a response that you have to return. There's a bunch of shortcuts to get to it, but in the end, it has to be an HTTP response that encapsulates your, the content of your response, the content type of your response, automatically figures out headers like the content length, that sort of stuff. And what we did here was use Python's JSON dumper to dump this dictionary to JSON. And so it's currently, it's empty. Let's see what it looks like in the browser once we add it to our URLs. Right, so, yay, we have a basic response. This is the format of the URL that will actually be requested again. It'll be crime.json with a get variable containing the bounding box. All right, back to our views. Now we have to actually fill this in. How are we going to do that? Well, I will write a quick helper function to convert a crime to a GeoJSON object. All right, so we have this function, it's rather boilerplatey, where it takes a crime object, it creates this specifically formatted dict that we need, it passes in the crime coordinates and the description into the dictionary, which will eventually be dumped out here when we do Everybody following that? So by the end of this, features will be an array of dictionaries that look like this, one for each crime in the bounding box. So hopefully this is still empty. Cool. And we can plug it into our front end. So like I mentioned before, we're going to be using jQuery to actually get the JSON from the server, and then we'll be using a leaflet function called add geojson on the map, which will add that geojson to the map. I will copy paste some more of this JavaScript since it's not super interesting. I'll break this up a bit. All right, so I won't dig in too deep into this unless anybody's super interested, but we are getting a bounding box. The map, the leaflet map has a function called getBounds, which will get us a bounds object. That bounds object has a method toBboxString, which gives us a string that looks exactly like the one that we need here. We're going to be tying that to a event listener on the map. So that's actually a really good question. The question was, who is actually going to be calling this function crime refresh? And the answer to that is, once we finish writing this function, we'll bind it as a listener, or as a handler on event listeners for when the user pans the map. So every single time the user pans a map, we'll do another query that passes in the bounding box, gets all of the crimes for it, and throws them onto a map. All right, 3 new lines. We have a crime layer that accepts GeoJSON. We add the GeoJSON to that layer. And to the map, we add that layer. That's a really good question. The question was, do you have to remove the layer that was there before? And yes, you do. So once we go ahead and actually load this, I'm going to pan around a few times. It'll keep adding the same points to the map, and it'll slow down pretty quickly. So we can take a look at that, and then we can remove the duplicates in just a sec. So this is the listener. When the map is done moving, it'll actually call crime refresh. Let's see if this works. Oh, hey, no. Are you sure on leaflet? Oh. Nope. There you go. Millions of dots. And so you can see I'm trying to drag right now. And it's dying because it's adding 10,000 dots to this every single time I drag. In like 5 seconds, you'll hear my air crying for help through its fan. Cool. So for starters, let's actually make the zoom level tighter so we see less of this. All right, so the map loads. It does not actually fire a move end event when it loads, so we have to drag it a little bit. We'll fix that in just a sec. And there are all your points. You can't click on them yet. It doesn't do anything. You just see them, and they're giant, ugly markers, but hey, we have stuff on a map. To fix it not loading the crimes on load, we'll just call crime refresh once on load. And again, we refresh. Hopefully, crimes will load up. There you go. Step one. Nice seeing you all. Thanks for coming. Let's take a break. This is a good time to take a break. Back in 7 minutes. 2:56. Ready to get started again? Got some coffee? Got some caffeine? Y'all look as awake as I feel. By the way, I have a URL or something here. Yes, that is the GitHub URL for the project that I'm working out of. So if you wanted to skip ahead or something of that sort, you can just hit that. All right, so now that we're back, I would like to talk about something near and dear to my heart, and that is map projections. Some of you may know what map projections are if you come from a cartography background. I came from a web background, and so I had no idea what these were. The basic gist of what a map projection is that you have a 3D globe that you're starting out with. It's a sphere. Thank you. You have a sphere that you're starting out with, and you want to turn that sphere into a two-dimensional map, usually a rectangular map. Now, that's not a perfect mapping, right? If you were to take your spinning globe and peel off the top of it, the sticker on top of it, and lay it down, it wouldn't be a perfect rectangle at all. And so some amount of fudging has to be done at different parts of the map to be able to make that translation work. I don't know if you guys have ever had Terry's chocolate. It's the kind where like you smack it on something, it's really satisfying, it breaks up and tastes like oranges and chocolate. It's delicious. But I don't know if you've ever noticed, like if you look at the actual wrapping of it, it's a little bit warped because the wrapper on it is a rectangular wrapper being wrapped around a globe, essentially. And that's what happens to a map projection, is when you take that wrapper off, if it's gonna be a rectangle, it has to be warped in some way. Either the areas of land masses have to be different, or 2 points, the distance between them cannot be linear anymore, or something has to be weird about the projection for it to fit onto a map. As this demonstrates, you have a projection that you wrap around the globe. You can see that it warps it around. Things would be actually a lot easier if we lived on a cube of some sort rather than a sphere. I don't know if you guys saw this post a little while ago somebody made about what it would be like to live on a cube, like if the Earth was a cube. It was super interesting. I mean, if you think about it, the reason that we're a sphere is because gravity's pull is equal in all directions. But if we were a cube, that would no longer be the case. You'd have, as you went up the edge of a cube, you'd have a crazy, the largest mountain that you can ever imagine. And when you got to the top of this mountain, which is basically impossible with gravity, but if you were at the top of it, you could look down the other side and basically see straight across. You know, there's no horizon, none of that, because you can see the entire face all the way down. And all of the oceans would end up puddling right in the middle of each one of those cube faces, because that's where the gravity is the most. It's really interesting. The number that I read was if you were on top of one of the edges, you could see 6,400 miles to the other side, straight shot. Kind of cool. Anyway, coming back to our boring spherical Earth, the projection that we use most often is called spherical Mercator. And that's a distorted projection. This doesn't usually affect you in day-to-day life, but it's worth knowing, especially if you have requirements that require you to care about it. Something like so this is a map of the world, as you may know. You can see that the land masses, for example, Greenland is roughly as big as Africa, maybe even a little bit bigger. But in real life, Africa is 14 times larger than Greenland. The further away you go from the equator, the more distorted land masses get. And so since Africa is right on the equator, it's squished up a little bit more. Since Greenland is far away from the equator, it's expanded out a little bit more. And so when you look at this map, you can see that, or you think that Greenland is roughly the same size as Africa, when in fact, the 14 times difference. It's huge. And this comes into play a lot when you're doing data visualization on maps. Say, for example, you were coloring each of these countries based on something, poverty rate or whatever you want. If you were to color Greenland one color and Africa another color, the eye would think that both of those have the same amount of weight, when in fact Greenland is tiny compared to Africa. So it's something to keep in mind when you're doing visualizations and things like that on maps. Your projection is not perfect at all. Alaska as well here looks ginormous when, like, Brazil is 5 times larger than Australia, than Alaska, but Alaska looks ginormous here. The other interesting property of having a spherical Earth is that when you're looking at a piece of paper, when you're looking at a spherical Mercator projection on a piece of paper, if you want to find the shortest distance between 2 points, you'd be tempted to draw a line, when in fact that is not the shortest distance. Here, if you wanted to go between Africa and the United States, and you drew a line using a ruler, taking that path is actually not the shortest path between those 2 points, because the Earth is a sphere, and so the real shortest path is the cross-section of the sphere, and it ends up being an arc. I'll show you what that looks like. So this is an interesting library, powered by Leaflet as well. It's called arc.js, and it lets you calculate the shortest distance between any 2 points. So for example, if you wanted to go from here to here, that is the shortest path between those 2 points on Earth. So this really shows off the kind of inaccuracies that you deal with spherical Mercator. In the vast majority of cases, you don't even notice this, but maybe you notice it when you're looking at, like when you're on a flight, international flight, you're looking at the in-flight display, and you see that the path you took was curvy, and you get annoyed because why didn't you take a straight path? Happened to me before. So yeah, interesting things about our Earth. Bringing this back to what we were talking about earlier, PostGIS recently added support for what is called a geography data type. All of the data types that we've seen so far, the points, the lines, the polygons, those are geometry data types. They're used in algebra, in trigonometry, all of those, because they're geometry data types. And we're lucky that latitudes and longitudes map really well to that. And because of that, we can deal with things like using a straight line to calculate the distance between 2 points. When in reality, if those 2 points represent geography rather than geometry, the shortest distance is not the length of the line, it's the length of the arc between the two. So PostGIS recently added a flag called geography equals true that you can set on your fields that will use a geography field rather than a geometry field. So once again, if you set geography equals true on, for example, your points field or on your polygon field. It will do geography calculations on it rather than geometry calculations, which are a fair bit slower. So you don't want to do that willy-nilly. But the way that it would really help, if you remember from this demo that we were just looking at, the longer the line, the more pronounced the arc is. And so if your data set is very well situated locally, a line is a really good approximation of the distance between the two. But if your data set is varied, and you'll often be trying to find the distance between a point in the United States and a point in Africa, you would be much better served with a geography data type. Something to think about. Back to our map sandwich. When we last saw our hero, we had 1 million points on a map, and it looked kind of ugly. So let's make it look better. All right, so this, you are actually at a conference called PyCon, so I don't want to dig too deep into the JavaScript. I'm going to lightly touch on styling of these and basically what you need to do and what you need to override to make these markers look a little bit more sane. But if you're interested in learning more about that, ask me some questions about it, and I can go deeper into it. But our first order of business is to change these markers, the markers that we're using for every single individual point. We don't want them to be so big. We'd prefer them not to be images at all. It'd be nice if they were circles drawn on a canvas or something like that. And so we want to get rid of the images. We want to make them much smaller. We want to try and make them maybe a little bit transparent so we can see a little bit better when multiple crimes happen near the same place. These multiple things that are somewhat opaque, rather somewhat transparent on top of each other will be more opaque, so on and so forth. Let's dig back into the code. Back to the JavaScript. And the place where we actually define what the markers look like is within this crime layer. So I'm going to refactor this slightly, move this out. So if you remember, crime refresh is the function that gets called every time we drag the map around. And so now that this is outside of that function, we still add GeoJSON to this, but now we actually only have one layer that we add all of that to. So this is also the first step to fixing the problem that this gentleman brought up earlier about re-adding the same points to the same map over and over again. It doesn't quite fix it yet, because Leafless does not actually automatically dedupe these things, but it's the first step. And we'll get to that in just a sec. So to style what this layer looks like, we do a couple of things. First, another bit of magic here, we can pass in an option to the GeoJSON object called point2layer. And this option is, it's a function that you're passing in that will get called every single time Leaflet is converting a point, which is a latitude and longitude from the GeoJSON, into a marker, which is their definition of a layer. So we're just going to override that function, and we're going to have it return something that's not a marker. We're going to have it return a circle. All right, so how did I do this? Where did this come from? Turns out Leaflet has documentation. And so if you want to learn what those things do further, you can look at their documentation on their site. The important part that you're looking at is one, lmarker, which is the actual class of which is instantiated for every single marker. We changed that lmarker to instead return a circle. So the first argument was a lat long, the second one was a radius of the circle, and the third was a dictionary of options. So in this case, we pass in a color option. Cool, so if we did this correctly, every single time we add more GeoJSON to this layer, for every single dot this will be called, it'll return a circle, and maybe we won't have these, oh, wrong one. Maybe we won't have these giant markers anymore. The yellow dots. The interesting part is you can actually right-click on this, inspect it. It's a object just like everything else. And so leaflet.clickable is the class on that one. We can do something like this should hopefully work. Nope, I might have gotten the class name wrong. Leaflet dash. Yeah, that was a random aside. I figured that would work. I'm pretty sure I just had a typo or something. Anyway. Maybe. This is what it's like to pair program with me. That is not red. That is the exact opposite of red. Oh well. I'll come back to that. I'll debug that. Anyway, back to this. We have dots. We still can't click on them. And we still add doubles every time we pan. So a couple pans. We should do something about that. And the easiest solution to this is a dumb solution, which is just keep track of what crime IDs we've seen and not to add them, not to add more GeoJSON when we find the crime ID that we've already seen. I suppose you could. You'd have to keep. Yeah. You'd have to keep it in the session. Who asked that? I didn't actually see anybody. Oh, thanks. The question was, can you keep track on the server side what dots a person has seen, and then for subsequent requests only return the subset of dots that they have not yet seen? And actually, I would say no to that because, for example, if the user refreshes the page, it's impossible to tell, roughly impossible to tell that they've refreshed it rather than they're just panning around. So we're iterating over every single one of the features. And instead of adding the entire thing, we'll add each individual feature one at a time. Now, important to note, this does not actually add the features one at a time, so to speak. It actually bunches them together. And the reason for that is we're adding them to a layer rather than adding them to the map itself. So if we're doing something like that, it would actually add them for reals every single time. But because of this, it has like nice bunching capabilities. And this is no slower than adding them all in one go. All right, so this is pretty simple. We iterate over every single feature. We dedupe on feature.id. ID is a field that we should send back, that we're not yet. So every single feature now has an ID field called crime that is filled with the primary key of the crime. And we are deduping this array based on that ID. Or rather, not deduping it, but not adding dupes to it in the first place.
Should feature be singular in your ID adjacent?
Yes. Thank you. My human compilers. All right. Hey, that's much nicer. It's actually log. Oh, that was a terrible idea. There we go. So as we pan, some more features are pulled in, but the ones that are already there are not added again. Cool. All right, that's a pretty good start. We can do one more thing before we move on from this, and that is have a pop up when we click on these dots. Right now, nothing happens. We could, if we wanted to, set the clickable attribute on this marker to false, so we won't get this little arrow and, or rather the pointer, and click events won't be propagated anymore, and we can have a nice static map that looks like it was baked server side, when in fact it was done client side. But we do actually want some interactivity on this. And so we're going to go ahead and add some code to it to show us a pop-up every time. And for that, we will listen to another event, once again on the crime layer. The event is called feature parse. That's the event that's fired every single time one of the features in the GeoJSON is parsed. And what we'll end up doing is bind on that feature a click event. So E is the event, which will always be the feature. On that feature, we bind a pop-up, and the value of the pop-up will be the description from our view, right here. Huzzah. This is another thing that can be styled with CSS, this entire pop-up box. You can actually look at the leaflet CSS file that we included a while ago, way up here at the top, and modify it to your own needs if you want it to look different. Cool. Any questions? Yes.
I was wondering if your leaflet will help with clustering or if you're going to be clustering.
Cool. The question is if Leaflet will help with clustering, and Leaflet will not, but there's a number of JavaScript libraries that will. that play very well with Leaflet. For example, D3 supports k-means clustering very easily. And so you can plug that in, and rather than adding the GeoJSON directly, you'll add points from D3 manually to the map. Cool. So I'm pretty happy with the dots at this point. We can leave them as they are and maybe come back to them later if we have time. Step 2, we're going to do the base map. So this nice looking Midnight Commander theme is one that's available from CloudMade for free. It's actually very easy to set up. And so I will go ahead and do that quickly, and then I will talk about it. So if you remember these three numbers, the 997 was the style. We can just change the style. Hit refresh. The URL for all of the base map images will be different. And ta-da, it's all different now. So once again, what we changed was in the tile layer, we pass in a URL that represents the URL to all of our base map tiles, all of the images that represent, that are on the bottom here. Yes? Yeah, so I can actually do that pretty easily here. So what I'm doing here is creating a dictionary with multiple URLs. There's one. Another one I like is called Pale Dawn. I think it's like 6 maybe. Oh, was it 8? Nice. Whoops. So layers.midnight is the URL to the layer that we were just looking at. And it's still there. Change it to Pale Dawn. Another nice style for more darker dots. And so yes, to answer your question, we can definitely make it a variable and pass it in. We can also let the user pick their style by hooking it up to, for example, a jQuery control that on change it will actually remove the layer there and add the new one in. Oh, that's cool. I'm told Leaflet has a control as well that lets you swap out the styles dynamically. All right. So we changed this, and we got a brief view of what it feels like to check out the other styles. One really popular strategy that's come around recently is making your own base tiles. So you're actually getting the data, the individual XML data for each one of these roads and all of that yourself from OSM, OpenStreetMap, and plugging it into something and baking your own tiles like this. So you're actually doing everything from downloading gigabytes and gigabytes of road data, you're feeding it into whatever tool you're using, you're generating the images, 256 by 256 images, and then storing them yourself and serving them yourself using CloudMade or something of that sort. And that's actually a really fun thing to do. It lets you modify a lot of really cool stuff. For example, if you're not happy with the labels on this, I personally hate the labels. None of you guys can read what the labels are. They're tiny. I could actually, if this was, if I knew what the styles for this actual map were, which I do, I can go in, change it, make each of these label texts bigger, bake my own set, and point the layer to my own set, and get a map that's fully customized to exactly what I need. It doesn't have to have things like BART stations and hospitals and public transit stops and all of those, it can be a nice, clean, simple map. And a lot of people have been doing that lately using a tool called TileMill. It is, definitely. So how you do that is you'd create 2 layers. You'd create one layer that's on top, which will be your San Francisco layer, and that layer should either 404 or return transparent tiles for areas outside of San Francisco. So TileMill is a especially impressive toolkit for styling your own maps. It's out of a company, again, Development Seed. We saw their product Wax a little while back. That was the JavaScript library that we were taking a look at. And they've built a UI for actually styling maps on the fly. It uses a language called Carto, which looks a lot like CSS. And it'll combine CSS, that Carto CSS with map data, for example, OSM data or your own data, and give you this nice looking clean map. Well, not this one, but a nice looking clean map. So these are all of the sample projects that come with TileMill. I'm just going to touch on them really briefly. If you've ever used Sass or Compass or any CSS framework, you're familiar with what it's like to have variables in CSS. So for example, if we wanted all the land to be black, we'd change that. It'll regenerate it on the fly. So it's actually very addictive going through here, tweaking stuff, figuring out what the CSS selectors are to, for example, make text bigger, make it look nice. And once you're done with it, the reason that they built it was their service is that you can send this straight to their servers, send your style straight to their servers, and they'll handle all of the generation for you. So you don't actually have to generate the individual tiles yourself. Just give them the style, they'll give you an endpoint. That endpoint will generate the tiles for you. You don't have to do that. They're actually a very open source friendly company. And this entire tool is open source. So the format that it sends is a format called MB tiles, which is literally a SQLite database that will actually have all of the tiles in it. And so if you wanted to, you can actually create your own backend for this and feed this directly to your own backend and that sort of stuff if you don't want to pay them for it. But yes, if you want to make your own tiles, this is a fantastic option that lets you tweak a lot without having to learn the intricacies of what's behind this. Now would actually be a good time to talk about what is behind this. It's a few packages, the primary of which is called Mapnik. We won't be going into Mapnik today. It's a monolithic, huge package for making whatever sorts of maps that you want to. You can look into it a little bit more. This is basically like a nice front end on top of Mapnik. Mapnik lets you pass in things like Carto CSS with a bunch of plugins, and it'll spit out these sort of maps, but you have to put a lot of stuff in front of it to actually make that easy. Anyway, check it out. It's called TileMill. It's worth downloading and playing with. It actually supports loading in your own data as well. Oops. I can actually try that. Zoom into San Francisco here. A little nubbin of San Francisco. If you wanted to actually see streets here, you'd want to download a dump of OSM, OpenStreetMaps, which contains that data and load it into here. We might do that if we have time later on. But before that, we can add a layer. So you remember we saw folders for blocks and for water under the data directory way back in the start. This is the shapefile for those blocks. So I'm actually going to load this into TileMill just to see what it looks like. I'll give it an ID called blocks. And this is like a CSS ID. I'll hit save. I will give it a red outline, and we can see exactly what's inside that shapefile. Now I just gave it a red color, so it's super ugly. But it's nice to eyeball the data that you have. This is the block data that we'll be using to actually create heat maps shortly. Let's do one more. So this was the water one that I promised I'd explain what it was. It is, as you'd expect, shapefiles of the watery area outside of San Francisco. If we look back to what we want the final product to look like, if I still have it open, yes. You can see that there's a nice clipping right around where the water starts for our heat map. And that's actually surprisingly painful to do. The blocks that you get from the census they extend out way into the water. And if you were to just draw those blocks verbatim, you'd have blocks reaching all the way out, like basically this far into the water. And so the reason that a water shapefile is useful is because we can filter out those blocks that are only water. What about pirates is the question. They will have to deal. Excellent question. I would like to tell you that right now. Let's see. So the U.S. Census publishes a bunch of shapefiles that have all sorts of things. They publish the interesting things that they publish are block data for the entire United States, census tract data for the entire United States, county shapefiles, zip shapefiles, school district shapefiles, school points, coastlines, water zones, rivers, a bunch of other stuff. And what they call it is the Tiger Line shapefiles. This is the dump from 2009, but they do it every year, and they have a different subset of data generally every single year. There was a huge dump recently in 2010, and that one is the one that most people use these days for things like counties and blocks. But it's all free. It's all open shapefiles. It's a very nice service. Tax dollars going to work. So that is one good data source. I also mentioned earlier I got the crime data for San Francisco from a site called San Francisco Crime Spotting. This exists for Oakland and stuff like that as well. But basically, they have a really nice API. They plug into, I guess so. They plug into police departments and directly get their data for crimes. And so it appears to be down at the moment for some reason. I'm just not going back far enough. But when I used it, I used their fantastic API, which does not have rate limits or anything, and just hammered the shit out of it until I got all the data that I wanted. I've been mentioning OSM a lot, OpenStreetMaps. It's, if you haven't heard of it, how many people have not heard of OpenStreetMaps here? All right, cool. I can explain it to you. Basically, the concept is people were unhappy with the fact that all of the cartography data in the world was owned by corporations. So Google considers it proprietary that they know where streets are, and that they know where oceans are, and things like that. So it's an open wiki project where anybody can contribute from their amateur GPS devices or even from memory what they think an area looks like. And it's resulted in an amazing, amazing database that's sometimes even more accurate than for-profit databases that you can use for free to create maps. And so basically, any maps that you generate yourself, you would probably be generating them from OpenStreetMaps data. And by maps, again, I mean the base map, which is the roads and things like that. So OSM is fantastic. Do check them out. The other interesting thing about OSM actually is they are expanding out into areas where it wouldn't make any business sense for companies to do, like completely remote and desolate areas in Africa where their main road is like a sand road, and that you can go on OSM and like zoom into it and see a road there, and like Google has nothing even close to that. So yes, OSM is cool. It was brought to my attention that I probably should have used OSM tiles rather than CloudMade for the first draft of the crime maps that we were just doing, because it would have been, there's no API key needed or anything like that. So I will do that next time in my next tutorial. A friend of mine, Mike Migursky from Stamen Design, he puts out these Metro extracts from the OSM database, which are really nice. So normally if you wanted to download the OSM data from the official source, you'd basically download 200 gigabytes of compressed data. You'd uncompress it, you'd go through it to figure out the area that you specifically want data for, you'd extract that out, you'd load it into your database, and then you'd do stuff with it. Luckily, a lot of nice people on the internet have done that for you, and this is one of them. You can go here and download just the data for example, San Francisco or Atlanta in a variety of formats. And to answer your question again, can you generate the tiles just for an area? This is perfect for that. If you're just generating the tiles for Atlanta, you don't need the OSM data for the entire world. You can just grab Atlanta's OSM data. I mentioned MapQuest earlier and was raving about them. MapQuest actually has a fantastic OSM server that you can query as an API to get OSM data for any arbitrary bounding box. It used to be before MapQuest that you had to deal with OSM's flaky XAPI server, Zappy server, that just went down a lot. It would ban you arbitrarily if you made 2 requests in like a day. It's horrible. So when MapQuest came along and created, basically as a service, they host OSM data, they host the API, and they keep it updated fairly regularly. It's been a godsend for people who just want to dynamically and arbitrarily regenerate maps for small areas. Speaking of updates, if you're not familiar with OSM, again, OSM publishes updates very often, like on a weekly basis, and they actually update things pretty well. So it's good to stick to updated data. Yes, I'm not super familiar with them, but I've heard of them. Oh, yeah, that's kind of cool. Satellite images, I guess. Anybody know about these? They look like satellite images. Maybe I'll play with that if we have time at the end of this. One more thing I want to mention. There's a GitHub repository called Acetate. Acetate is a style, a Carto CSS style for Mapnik. And this is a fantastic way to start working with something like Mapnik to generate your own tiles. If you're not going to use TileMill, if you want something more programmatic, you can basically just check out Acetate, plug it into a tool called TileStash, which we'll be playing with in just a second, and you can basically, and also point it to a OSM dump somewhere, and you can basically generate your own maps and split things up. One really interesting thing that that is on like my backlog if we have 2 more hours than what we actually do here is taking an OSM dump, loading it into a database, using Acetate, and then rendering the roads differently from the base map. And the result of that would be, rather than the heat map here overlaying on top of the roads and on top of the labels, all of the roads and labels would actually be on top of the heat map. And you would see the heat map colors underneath where like the ground would be. It looks really cool. I don't think we'll have time to do it this time, but maybe in the sequel. All right. So we're done with the base map. Step 2 is done. It's time to move on. Talked about data sources. Base map is done. Cool. Now we're on to the heat map. This is the more complicated part. It's not so much complicated as there's a lot of different libraries that we're combining here for this, as well as there's a little bit of magic that happens. Specifically, just to give you guys a heads up where the magic is, it's converting latitude and longitudes or tile coordinates, those two into pixel space. So when you're drawing on a 256 by 256 image, the top left is always 0, 0, bottom right is always 256, 256, no matter what the lat longs of those are. And so it's converting between those points and lat longs that requires use of a library that doesn't have the best API. And so it's like 8 lines of magic that you might not understand, probably just scaring you guys for no reason whatsoever right now. One thing that's worth noting before we dive in, the concept of heat map color scales. It turns out it actually matters what color space you use when generating your heat map color scale. Now the color scale that I'm talking about is what color means red, or rather, sorry, what color means dangerous, it's like a reddish hue. What color means safe, it's a greenish hue. And all of the colors in the middle. You'd think it's simple. You pick a red, you pick a green, and do a linear regression between the two based on what the numbers represent. But it's actually not that simple. The reason is, say you use RGB space. RGB space looks like a cube that's rotating up there. You pick a point inside that cube, and that's like the reddish color that you want. You pick another point inside that cube, and that's the greenish color that you want. You draw a line between the two, and that's like a nice gradient between red and green. You can do the same thing in a color cylinder, like for example HSL or HSV. Pick a point in the cylinder that you want for red, pick a point in the cylinder that you want for green, draw a line. The line's going to go through different colors depending on what color scale you picked. So again, in RGB, the color, the slightly less green color for this 90th percentile, that color will be a different green than the 90th percentile in an HSL scale. Does that make sense? Cool. Anyway, the long story short of heat map color scales is you just use HSL because RGB actually makes really horrible looking color scales. All right, let's dig into TileStash now. I've mentioned it a couple of times, but I will explain exactly what TileStash is in just a sec. All right, so I just created a folder called tile server and 3 files underneath that folder. And I'll explain to you why I did that. TileStash is a Python package that is one of the most essential parts of my toolkit when I'm making maps. It's basically the glue between all of these things that we've talked about so far. And makes a lot of stuff really easy. Things like say you have a large JPEG. Say you took an atlas, you scanned it in, you have a large JPEG. You want to overlay it on top of a real map, maybe with some opacity, and that'd be kind of cool. Tile Stash will let you do that in a few lines of configuration. Say you wanted to chop that JPEG up into tiles using the same format that we've seen so far, the Google XYZ format. Tile Stash will let you do that in a few lines again. If you're familiar with Tile Cache at all, Tile Stash is similar to that. Tile Stash will let you cache your files. And so, for example, when we refresh our heat map, or whichever tab that's in, when we refresh our heat map, every single time on every single request, it'll regenerate each PNG. We can automatically have Tile Stash cache those PNGs on S3, on disk, in memory, and return them when they're available, generate them when they're not. So again, going back to just generating tiles for San Francisco, it's actually really nice to set up Tile Stash and set up a cache. If all of your users are just hitting San Francisco, you'll never actually generate any of your tiles outside of that. And generating tiles is actually a fairly time-consuming process because it's a lot of files. Anyway, to say in short what Tile Stash does, Tile Stash takes a request that comes in on a URL that looks like a tile URL. So this URL that you see here, we have a layer name, which we'll get into in just a sec. We have the zoom, the X, and the Y, just like we saw before, and then a dot extension. It takes those requests. It gives you a way to figure out what tile that represents, what latitude and longitude that represents, what bounding box that represents. It gives you a chance to return the data in some nice format, and then it'll take over from there. So for our purposes, what we're actually going to be doing, what we're going to be using this for, is the translation between tile requests for the heat map into bounding boxes that will actually draw the heat map onto. I think it'll get more clear as we dive into it. So the root of all of this is a JSON file called tilestash.config. And this is where you define your layers. Each layer gets its own root in the URL. Like you saw, the layer name was the first part of the URL. So in this case, we'll just have one layer, which is the crime heat map. Interesting things you can do with multiple layers. Say you had one layer for the crime heat maps, which returns PNGs. Say you had another layer for roads that just returned roads in PNGs and everything else transparent. And then you had another layer for a base map, which doesn't have any roads on it. It just has terrain on it. You could, again, composite those three things together so that the terrain is on the bottom, the colored heat map is on top of the terrain, maybe with some amount of transparency, and the roads are on top of the colored heat map. And labels and all that are on top of it. So you can do those interesting things with Tile Stash, which are a little bit harder to do without it. So this is in the configuration, you have to define what you're going to use for your cache. We're just going to use a dummy cache, which means nothing will actually be cached. So this provider parameter is really where the magic happens. This is where you actually say where you want your data to come from. We're going to use a class provider, so it'll just call a method on that class for the data. we're going to call that class crime heat map provider, which we're going to put in providers.py, which we defined earlier. TileStash has a number of providers, which you can look in the documentation at. Some of the interesting ones, Mapnik. Like I mentioned earlier, you can plug in acetate into TileStash and generate your own tiles very quickly. You would do that using the Mapnik provider. You pass in the style.xml from from acetate, you pass in the path into here, make sure you have Mapnik installed. TileStash will handle everything for you, and you'll magically get a tile endpoint that you can plug into Leaflet or anywhere that will have your own generated tiles. Proxy just passes through. So for example, if you had a URL that had to access localhost, but you wanted to proxy through to OpenStreetMap tiles or something, you could use that. Not that interesting. Vector, which lets you tile GeoJSON data. We remember what GeoJSON is. It's a data format for transferring shapes from the back end to the front end. We can actually tile GeoJSON data just like we tile images. In our current example of crime maps, we return every single crime that we've found on every single drag of the box, which is kind of wasteful. If we were to actually tile that data, then on the server side, we would only be returning those tiles that the user hasn't seen yet, because the user would only be requesting those tiles that they haven't seen yet. And we wouldn't need any sort of deduping code. We wouldn't need any of that because we're just getting tiles again. I didn't do that because of the interest of time, but for the live crime maps site, that we do use that. We tile GeoJSON. The other benefit that it actually has is it's incredibly cacheable then. If you're requesting bounding boxes, you can't cache on the URL because there's a billion different bounding boxes that you could have. But if you start to turn it into tiles, you can cache each one of those tiles individually, which is really easy. And a bunch of other ones that you can take a look at the docs yourself. MB tiles, I think I mentioned that. That's out of TileMill. TileMill generates MB tiles, and you can serve them through TileStash and do composites on them and all that sort of stuff too. Anyway, we're going to be using the least hand-holding method, which is just having a class. That class has to implement a certain interface and it has to implement a certain interface and return a savable object. In 99% of cases, what that'll mean is a Python imaging library image. It has to return that. TileStash will call save on it. It'll do any post-processing it needs to do on there, and then it'll send it out. So when we create this class, crime heat map provider, we're going to be returning a PIL Python imaging library image out of there. The other interesting stuff it can do, because it's got that sort of interface, is it can do meta tiles. So for example, if you had a data set that's very expensive per query, meaning you wanted to reduce the number of queries basically, you could do a meta tile where if one tile in the middle of San Francisco is requested, it'll generate all of the tiles in one request for all of San Francisco. It'll split them up on the back end itself, store them in the right place, and subsequent requests to any of the tiles around it will go out to that. Yeah, let's dig in. The preview directive, it's just for convenience. It will add a URL to every single layer that lets you preview what it would look like. It basically gives you a very bare bones Slippy map that you can drag around with no other layers. That's just for convenience. It's lat long as my house. All right. Now we can go implement crime heat map provider. Is that not valid Python? Anybody see anything wrong with that? Might just be my linter acting up. But anyway, so here comes the magic that we were talking about. Basically, you create a class that has a method called render area. This is actually the advanced mode for this. The simple mode is render tile, which lets you just render one tile. Render area lets you render arbitrary sizes of tiles. So you can do bigger tiles, smaller tiles. You can do meta tiles like I was talking about. So it's just easier to always implement render area. What we first have to do is take this xmin, ymin, xmax, ymax, and zoom, and use it to get a set of to get a bounding box. Basically, this is what represents the tiles that we were rendering. We need to convert it to a bounding box. Now's a good time to cheat. All right. Here is what's happening. There's a library called Modest Maps, which works really well with tile stash. That's what we're using to actually convert the xmin, ymin, xmax, ymax into a bounding box with latitudes and longitudes. How we're doing that is by using a projection. Again, like I said in the start, tiles are all an algorithmic thing. OpenStreetMap implements the same algorithm as Google and everybody else. And so we use Modest Maps OpenStreetMap provider, which contains the algorithm, the math logic, to figure out this tile corresponds to these latitude and longitude coordinates. We then use self.layer, which is provided to us by TileStash, the Modest Maps object, to project it. We get the bounds for it. I'll move this out. We again do more magic with Modest Maps, which eventually leaves us with this object mmap. Mmap is what we will finally use to figure out that this latitude and longitude pair corresponds to this x and y pair in pixel space. So again, our blocks are stored as latitudes and longitudes in our database, and that's how we'll be looking at them here. We need to map them somehow into pixel space such that we know what any arbitrary pixel inside the tile represents in real world space. mmap lets us do that. And you'll see the function that I call in just a sec to actually do that. We're back to bounding box again. We remember this from the view that we made. We made a bounding box from the 4 coordinates. From VBox takes x comma y, not lat comma lon, which is why we're doing min lon comma min lat. Once again, the bane of my existence. So the nice part about all of this code that we've written so far here, all of this is boilerplate. This is going to be identical in any heat map provider that you ever make. This is where it starts getting interesting. What we have now is a Python imaging library image that we're drawing onto. we have a bounding box for which we need data. And we can go ahead and start doing that. So for all of the blocks in our database, that will load in just a sec. For all of the blocks in our database, we're going to grab all of the blocks. We're going to draw things with them. So a modestmaps.geo.location object represents a latitude and longitude. So we pass in the latitude and longitudes for each point in the exterior of the block's polygon, i.e. magic. We convert it to pixel space. And we add that tuple to a list. So hopefully we have a list that's the exterior of the block that we're drawing in pixel space rather than in latitudes and longitudes. So we'll come back to this in just a second. There's one thing we need to do before this will actually have any hope of working, and that's actually creating blocks. I created a new Django app for blocks. I'm going to do the same thing I did with crime here. This time it's a polygon field instead of a point field. Same overriding of the geo manager. And that's probably it. Sync DB. Forgot the same thing I did last time, which is adding the app here. All right, now we have a blocks.block in our database. And we need to load the shapefile that we looked at here a little while ago in TileMill. We need to load that shapefile into our database. And the interesting part here is we're converting a shapefile and all of the shapes inside of it into something that we can save using GeoDjango into Postgres. How will we do that? The general style is to put that code in a file called load.py in your Python, in your Django application. Django comes with a tool called layer mapping that lets us load blocks. And so to recap, what we're doing here is we are taking blocks out of the shape files that we got from the census. We're loading them into our database so that in a sec we can generate heat maps based on those blocks. So the heat maps that we're generating is actually filling blocks. I might not have mentioned this actually, this might be important. The heat maps that we're generating, we're filling blocks on the actual map. We're not doing fluid heat maps. We're doing heat maps that snap to the edges of blocks. The reason for that, and I can go into great detail for that, but it's mostly a stylistic reason and a practicality reason, in that people are more interested in that sort of data, and it's more readable data. Most heat maps that you see are very fluid, very soft, very bulbous things on the map. They often cover up interesting trends in the data. For example, with crime, one of the interesting things that we noticed was that there were a number of blocks within fairly dangerous neighborhoods that were comparatively safe. That sort of thing is very interesting to people like me. I love to see that that sort of disparity exists. You can look right here in the middle of the tenderloin. Might be a little bit hard to see with the blocks and all that. And I don't have the server running anymore, so this won't refresh. But there was a little spot there that was slightly green amongst a sea of red, slightly orange rather. And those sort of trends are really interesting, and those sort of trends are hidden when you smooth out a map, heat map, by using most general techniques. So the long and short of it is the heat maps that we're generating are filling in blocks, individual blocks, census blocks, with a color as to how dangerous that block is. And when combined with all the other blocks, it makes for a nice looking heat map that's interesting, that gives you general trends, like this neighborhood is very dangerous, but doesn't rob you of more interesting micro trends within the neighborhood. Back to what we're doing right now. We just created a model called block. We're gonna load blocks from the census into our database, and then we'll be back on track. So layer mapping is the tool that we'll actually use. It lets us create a mapping between a field inside a shapefile, namely this capital polygon field inside the shapefile that's defined by this path, and map it into a field on our model, namely poly, on the block model. This is really well covered in the tutorial for GeoDjango, so that can explain it way better than I can as to what's actually going on behind there. But we can go ahead and run this real quick. And so right now, it's going into the shapefile for blocks that I already downloaded, loading it into the database. And if it worked, we have 7,400 blocks in San Francisco. Coming back to providers.py, when we were last here, we got all of the blocks within our bounding box. We got their shapes converted from latitudes and longitudes into pixel space. Now it's time to do their color. Now, if you remember, color should be based on how many crimes are within that block. And so that's luckily a nice and simple query again. It's all of the crimes that have a point within block polygon. So we have, for every single block, we now have its shape. We have the number of crimes within that block. Now we get into the heat map scale that I was talking about, where we have a green and we have a red. We need to define what means green and what means red, mainly how many crimes within a block means red and how many crimes means green. And I did some data analysis on this already and figured out good numbers for it. By data analysis, I mean I just tweaked it until it looks good. And by tweaked it, I mean I tried the first thing and it worked great. So these are HSL colors, hue, saturation, lightness, for green and for red. If a single block has less than 5 crimes, we'll go ahead and call it green. If a single block has more than 15 crimes, we'll go ahead and call it red, and do a linear scale between the two. As soon as we have the color, we're going to draw this onto the pill map. So this is a simple formula, the scale. Can everybody see that low, by the way? Should I bump that up? This is a simple formula that will give us a scale that we can multiply the color by. So the exact middle between 5 and 15 will make scale equal 0.5, which means we can scale each channel in the color individually by 0.5 and get the color between green and red. So we'll do that right now. So this is just an elaborate way to say, for every single one of the channels in the colors, for hue, for saturation, and for lightness, scale it based on what point between green and red we want it. And after all of that, we will have H, S, and L values, which we can then assign to variable. Saturation and lightness are represented in percentages. Hue is an absolute number. Let's close it all and actually draw this polygon. Locks was the array that we created earlier with all of the points. Huh. How embarrassing. All right. So for each block, once again, we figure out the shape, we figure out the color, we draw that onto a pill map. Once we figure out the color, we draw it. And once we've drawn all of the blocks, we return that map. And hopefully Tile-Stash will take it over from there. So I will do a little bit of path hackery just to get Tile-Stash running here real quick. So how that works is, I mean, normally you'd put both of these, the Django server and the Tile-Stash server, under the same WSGI application on different paths. I'm just using both of the individual test runners, or rather test servers. So I did a little bit of path hackery that meant I can run both of them together. Now the Tile-Stash server is running on port 8080. The original Django server, which has been running this entire time, is on port 8000. We passed in the config file, tilestash.cfg, which we made a little while ago. And if everything goes well, we should be able to use the preview for this tile layer to see this immediately. That's what it looks like when we don't have any data. Oh no, I see. Block color is there. Once again, pair programming with Zain. All right, looks like it may be working. Sweet. So this is no base map, no points, just a very simple preview. Each one of those tiles is being individually generated on my overheating MacBook Air right now. But as you can see, you can almost make out like the boundary of San Francisco right here. That, remember what I said about the water blocks? All these blocks go way into the water. And that's a little dangerous area in the Tenderloin. That is what a simple heat map looks like. Our last task is to throw this as a layer into Leaflet and style it such that it's got some amount of transparency so you can see everything underneath it. The reason that they're not cached is because in our config, we just use this. It would be as easy as doing that to start caching them. I can actually do that. Right, let's actually give it a path. I think that should work. So it'll generate them one more time. And hopefully after that, they'll be cached. Another thing I like to do, which I might do in a sec, is use gUnicorn instead of the built-in dev server, just because I can add more workers. Because this is entirely single-threaded right now. Yep.
Strategy of using tiles instead of using heat maps. Could you have also just done that with Leaflet and polygons that are embedded? Can you fill in the polygons?
You can indeed. The problem is, again, performance. When you have, so this is 8,000 polygons. Each polygon has on the order of 5 to 10 points within it that define it. When you're drawing that many vertices, you're going to have performance problems very quickly. The other thing is, how do you get that data to Leaflet? It's fine when you're just doing San Francisco. That's what we're doing with the crime dots. We're sending the entire thing in one request. But say you wanted to do crime maps for all of the United States, you need to chunk it out somehow. And tiles are the most efficient way to do that.
I'm just wondering if deciding whether something should be done in the tile layer or whether it should be done on software or market or whatever, is that all the trade-off you're all thinking about when you're designing map applications?
I would say that performance is by far the primary reason. The other thing is interactivity. It's much harder / impossible to interact with these on the front end. So I can't actually interact with any of these. There's interesting ways around it that we've done. For example, one of the things that we actually have done is to draw these on the client side is rather than coloring these on the server side, we actually send block ID tiles. And so every single block would be uniquely colored within this. And then we send that unique color along with a value, a heat map value to the front end. What that lets us do is run an operation on Canvas that says, find all of the pixels with this color and recolor them to another color. That's actually really efficient as compared to drawing vector blocks. And so with that, we've actually had very efficient client-side rendering of heat maps. And we've actually been able to do some interesting stuff. Maybe I can show you something. Just as a quick aside. So this is a tech demo, basically, that we did. If it is still up, yes. This is transit times from Trulia's offices to anywhere in San Francisco via public transit. And the interesting part is that all of this is rendered on the client side, which lets us do things like this. And since it's all rendered on the client side, you can change the colors dynamically based on user input and things like that as well. Anyway, let's get this into... these are tiles. So what this is backed by is actually each individual block here is uniquely colored in a image tile. And Canvas lets us redraw that unique color to another color.
So the hover is just based on the document.
Right. There's another version of the same idea for commute that we're currently exploring. And I don't actually think it's public, so I might not show you guys. But the idea for that is actually storing more than just a block ID in those underlying tiles. It's actually storing the commute time in those underlying tiles. And so the nice part about that is you get these tooltips for free, and you get interactivity for free, because when, for example, the user clicks on a block, you just have to look at the color of that block to figure out how long it takes to get there. And you can show that in the tooltip. So you're encoding data in the color, basically. We have all three things on the same map now. The heat map has no opacity, so you can't actually see the base map layer. That's easily solved.
How is it that you're seeing the crime data?
Because we added it as a layer afterwards, so it actually stacks on top of each other. It's a good question. Forgot to repeat it. Question is, why can you see crime data on top of the heat map when you can't see the base map? Sweet. And my laptop is generating all of these, so it is a little slow. But if you were to throw this on a server, it's actually quite fast.
What would the strategy be if, like, the crime data was updating, so you get it every hour, every 12 hours, or something like that? So you wanted to somehow cache it while it's valid, but then, rebuild that cache.
Right. So we actually do that, and we do it with like the standard cache busting of adding a get variable at the end of the JSON URL. So yeah, there you go. I don't think we have time to nuke the water blocks, but I think you can get the idea. Basically, you load in the shapes of water, and you delete all the blocks that are within those water shapes. And you get the nice clipping that we saw earlier along the lines of water. But yeah, there you go. These are clickable dots, a few thousand of them on screen at the same time, with a heat map layer underneath that can be dynamically generated based on those. Everything can be styled with CSS. Questions? Yeah.
You talked about using acetate with mapping.
Mhm.
What would be the advantage of using that over doing something like using tile mill to export the mapping XML file?
It's programmatic, basically. Tile mill is a very manual thing. It's something that you'd want to use once. Yes, repeat the question. Why would you want to use mapnik with tile stash rather than exporting? I'm sorry. Why would you want to use acetate with tile stash rather than exporting a tile mill style into mapnik? Is that right? Yeah, it's programmatic, and as well as acetate's like a nice, good-looking style that I'd want to use. You can go check the preview. Did that answer your question? Cool. Yes. So the question is, how is the support of rendering and projections other than spherical Mercator? In JavaScript libraries, it's somewhat okay. I heard during the break that Leaflet comes with like 1 or 2 other projections, and everything else you have to implement yourself. On the back end, GeoDjango is actually perfectly okay with any projection, since it passes it onto the database anyway. Into your model fields, your point fields and your polygon fields, you can pass in a SRID argument for the projection that you're using. And it actually has some interesting support, like in the layer mapping, to automatically transform projections from, like for example, if a shapefile that you're importing is a different projection than your models, it'll automatically transform those projections, and as well as on the way out. So it's a little bit of help for that. And for rendering tiles, you're basically using GeoDjango's ORM for fetching data from the database. So it's roughly the same for rendering tiles. Yes?
What's the performance of PostGIS? Is there any way to, where you need to cache things like responses for all the crime pointers with the shift and import? I mean, because it seems fairly unlikely. It seems like you would get a lot of requests from different positions, different zoom levels and stuff like that. Is it reasonable to try to cache that information?
It's definitely reasonable. That would be like one of the strategies for caching that would be to tile the data rather than doing it on every single bounding box. You tile the data and you can cache each one of those. As far as what performance is like on Postgres and PostGIS, it's not much slower than just the normal database itself. So like you automatically, GeoDjango adds a spatial index on every single spatial field that you add. And the spatial index uses an R tree in the backend, which is blazingly fast. The usual caveats apply if you're doing an n times n query. It'll still be slow, but it's not too bad. Yeah.
Do you have much luck importing raster data?
Have I had luck importing raster data into TileMill? I have not. I haven't actually tried it. No. No, I don't have personal experience, sorry. Yes?
Do you have anything with elevations, terrain maps, or?
Not terrain maps. I've played with elevations as a way to show more data on the map. There was a heat map that I made a little while ago that used elevation to show my spending at restaurants in San Francisco. And so like the higher the elevation, the more I spent there. And I used GeoDjango to store that data. GeoDjango, you can store 3D data in GeoDjango, so I just made it another axis. My end goal for it was actually to create a 3D printout of it, like in actual plastic, and color it. I couldn't find a 3D printer, so if anybody has access to that, that'd be awesome. Alrighty, thank you guys.